is a smaller proof used inside a bigger proof. Right? Now, one of the famous proofs of number theory is the, I write it down here, the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And that theorem says every integer can be uniquely factored into primes and their powers, the powers of primes. I'll give you an example. Take an integer, I don't know, 84, let's say, and we want to express that as a product of the powers of primes, and it can be done in only one way. So let's split that up. So that's like 2 by 42, right? And that's the same as 2 by 2 by 21. So we have 2 squared times, now that's 3 by 7. Now let's order the primes in increasing order. Okay? So let's tidy this up a little bit. So it's 2 to the 2 times 3 times 7. And that's the they're the factors of 84. And any integer can be factored uniquely, just in just one way, into prime numbers and powers, powers of prime numbers. So it's like power 1, power 1. Okay, that's a fundamental theorem, and we can use that in our proof for n. Remember, n was 2 by 3 p max plus 1. Now that is an integer, right? Product of integers plus 1, still an integer. This is an integer. Okay. Now, because it's an integer, all integers have a unique factorization into primes. That's been proven. I haven't proven it here. It's done elsewhere, but we're using it as a lemma in our proof. We're taking a smaller proof from elsewhere, bringing it into our proof, and using it. So this fundamental theorem of arithmetic says this n must be a factor of, is a product of primes, right? So it'll be p1, p2, whatever. Now these prime numbers here, they can't be any of these, right? Because this prime number, let's say that the p1 is not one of these, right? Because of this 1 over. So this p1 here must be larger than this p max. This whole thing must have a prime p1, but p1 must be bigger than this one. Does that seem obvious to you? Okay. And therefore, the assumption that there was a maximum is false, because this p1 has to be larger than that. Right? Because you can express this n in the form of prime numbers. That's what the fundamental theorem of arithmetic says. Okay? So this prime p1 is not one of these. This assumption here that maximum is p max must be false. So there must be a bigger prime. So p1 must be bigger than p max. Right? So we've got a contradiction, and therefore this assumption must be false. And if there's no maximum prime, therefore the number of primes is infinite. Okay, so done that. Alright, I'll stop.